explain the reason things are really complicated. You see, the covering numbers here, the space on which you observe things here is, I wrote it as L1 mu n. Okay? What matters here are the values of your functions on the fixed points x1 to xn which you sample. Now, the way you sample things is determined by your preset probability measure. Okay? So your probability measure might decide to give more weight to some samples than to others. Once you change the sample, this structure changes. Right? Instead of being interested on the values of the wave function class and on the point x1 to xn, you're now interested in the values of the points y1 to yn, which could be completely different, which could have completely different covering numbers. I mean, this isn't enough. You need to be able to bound this for every significant empirical measure. In other words, for every significant sample, in the sense that the original probability measure assigns enough weight on that sample. So this is a rough way of looking at it. Now, things are even worse, because remember, everything I did here, I fixed the probability measure. I fixed the probability measure. This is a fixed probability measure. You sample according to a fixed probability measure. But I don't know that probability measure. I'm given a problem without any prior knowledge of the probability measure. So what in fact I have here is not the expectation with respect to the probability measure of this. That's fine. I have outside here the supremum over all probability measures. Okay? So in some sense, I can't hope in this approach, I can't hope that I just see nice samples. Because one probability measure can give me nice samples, but another one can give me nasty samples, and I have to treat that one as well. So in fact, what I have is the supremum over all mu, which is what I was interested in, is bounded by the supremum over all mu of this. So everywhere you want to sample points, I should be able to have it. Okay, so the only way to do that seems to have the ability to treat every sample separately, right? You can't rely on the fact that your probability measure will help you to avoid nasty samples, because one probability measure will do that, but another one won't. So what you have to do is, in fact, compute this for every empirical measure, which leads us to the definition of uniform entropy numbers, uniform covering numbers. So, definition for every x greater than 0 and p between 1 and infinity, let np epsilon f n with the supremum over mu n of n epsilon. Very complicated looking, but it's really simple. What I'm saying is this. My goal is to show that this thing tends to 0. Right? I want to show that the probability of watching, having a nasty sample like this tends to 0 as n tends to infinity. This thing depends on n. So it could be conceivable that as I increase my sample size, I get very complicated sets, f of x1 to f of xn, with nested covering numbers, and that will destroy the fact that here I have a great decay. So here I have a very nice exponential decay, but if this increases too fast as a function of n, I have a problem. Okay, so I want to compute the way the covering numbers increase as a function of n. And I want to do it uniformly over all possible samples of length n. Right? So all I'm saying here is look at all the possible samples of length n, compute the covering numbers at a certain scale with respect to each sample of length n separately, and then take the worst case. Okay? And the p here is simply a way in which I want to be able to change the metrics. So in this case, all I care about is p equals 1, because I'm only interested in n equals 1. So these are called uniform, or these are called, not yet uniform, but, okay, these are uniform. What I would hope for is to get something which doesn't depend on n. Okay? There is a chance, perhaps, that for certain classes of functions, this expression will not depend on n. They will be uniform regardless of the size of the sample. So in some sense, the size of the class doesn't increase by much as the class grows. Okay, so these are called uniform entropy numbers. So I denote by np epsilon f supremum over n supremum over u of n of n epsilon L. Okay. It's completely unclear whether I can do something like this. But it may be possible that this is always infinity, right? That for every class I take, no matter how simple it is, or for every interesting class, if I let the samples be horribly large, this will go on. Okay? But these are the two quantities I want to investigate. Of course, once I define this, I can always replace this expression, the expectation, by this expression, because this is the worst case. And the worst case is always larger than the average. Okay? So in general, what I have is that the supremum over all probability measures I start with, that supremum greater than epsilon is bounded by 8 times the L1 covering numbers. Let's get epsilon over 8 of length n e to the power minus n squared. Now, for anything to work, I need to bound this. So far, I just gave a sufficient condition to the ability to control empirical means, deviation of empirical means from the actual means. That's all I have. I haven't given you a single class of functions for which I know how to control this yet. Okay. Now, the work of Almond in the 70s, which I said was for Boolean classes of functions, got essentially the same result, maybe with different constants here, here, and here. But I don't care about those. But instead of the n, what I wrote in 1 here, they had an infinity, which is worse, because an infinity covering numbers are always larger than L1 covering numbers. Okay? Just as I said before. But now they wanted to show how to estimate something like this, or in their case, n infinity. Okay? And they wanted to see what property of Boolean classes of functions functions determines this in the case of an infinity. And what they did was introduce a property called VC dimension. And the funny thing is that exactly at the same time, well, they didn't call it the VC dimension, of course. We didn't call it the VC dimension after Vapnik and Chervonetis. But in exactly the same year, two other mathematicians did exactly the same work regarding this, what we call today the VC dimension. One was Sauer, the other one was Scheller, the logician. And the property they thought of was the following. The problem we have is the following. Okay, now suppose F is a class 0, 1, and they had a property, they defined a property which describes when a function shatters a set. What does it mean? A class function shatters a set. Now suppose you look at this set of points. Okay? This is x1, x2, x3, x4, x5. Now, every function, if I look at it at these points, I get a set of Boolean vectors, either 0, 1, every coordinate. When I look at the collection of all these Boolean vectors, I go over all the class F, I get a subset of the combinatorial Q. Okay? Vectors with n, or in this case with 5 coordinates with values between 0 and 1. Now, a way of measuring the richness of the class on this particular set is to ask whether or not I get the entire Q. Right? So, for every function you get, this is 0 and this is 1. So let's say you get, for one function you get this point, for another function you get some other combination. So each one of these vectors, so this is a vector which is 1, 0, 1, 0, 1, is an element in the combinatorial Q. I'm saying that the class, in some sense, is rich on this sample if I get the entire combinatorial Q. Okay? That's the definition. And the name for it is a sample being shattered. That's how we call it. So, a set Sn is shattered by F if this set, which is f of x1, f of xn, when I go over all the functions in F, is just a combinatorial. This is the notation of the combinatorial Q, simply minus 1, 1 to the power n. All possible combinations of minus 1, so 0. 0 to the power. Okay? So that's the definition of a sample being shattered. The VC dimension of F is the size of the largest set F and shadow. Okay? So in some sense, if you remember the idea I told you about projections, sort of coordinate projections, for every fixed example, this defines sort of a projection of your class onto this set of coordinates, which is these vectors, the set of vectors in Rn. If you get the entire combinatorial cube, you're large, and the way I measure how large you are is by saying what size of a sample of the set can you get? What's the largest dimension of a projection for which you can get the entire cube? Okay? Now, if you have the entire cube of dimension n, what's the minimal cardinality of your class? So you can get every combination of 0, 1, or n coordinates. So your cardinality of the class has to be at least 2 to the power n. Right? If you have a shattered class of dimension n, you have at least 2 to the power n different elements in your class. Now, so if this were the case, then here you have a really bad problem because you have something which grows exponentially. Now, assume that your class has a VC dimension, a finite VC dimension, right? Meaning that you can't get an entire cube of dimension larger than its VC dimension, let's call it D. It still doesn't tell you anything, right? It could be conceivable that you can't get the entire cube, but you can get almost the entire cube, maybe half the entire cube. It still would be 2 to the power n minus 1 elements, and still too large. But here came a very beautiful result, which I'm not going to prove. So this is the name of the statement depends on who you ask. Right? People in machine learning would say it's due to Bartholdi-Chervonetis. People in mathematics usually call it the Star-Rochelle effect. So that's all of them in 1971, published in completely different journals. So, assume that BC of F is D, then for every cycle Sn, the cardinality of the set fx1, fxn, fn is bounded by en over d to the power. Okay? So you start, all that you know is that you can't have a combinatorial cube of dimension larger than D, and you get that no matter how large a sample you take, the way its cardinality, if you look at these vectors, the way the cardinality depends on n is this way. This polynomial in n with exponent d, not exponential in n. So this restriction is very, very powerful. The proof isn't all that difficult. I'm not going to show it, but it's a really nice proof that everyone who's interested in machine learning should look at it. But this tells us a lot. Right? Look at what we want to show upstairs. We want to show that the cutting numbers of F with respect to L1 on a sample of size n are well behaved. Okay? Now, the covering numbers with respect to L1 are always bounded by the covering numbers with respect to L infinity. And the covering numbers with respect to L infinity are always bounded by the cardinality of the set, right? You can take all the set, this is a cover. So you can replace what's written upstairs by this. Okay? So essentially do graphic and geometrics. That's supreme over all probability measures. Greater than epsilon is bounded by, and I'm going to use a constant, excuse me. C, which is some absolute constant, n to the power d. And here you have e to the power minus n squared over 128. Okay. From this, you can easily get sample complexity estimates for VC classes. Right? All you want to do, right, the question is, when is this thing smaller than delta? So all you have to do is solve when it is smaller than delta and find a condition on n. And the condition you get, so what you get is that some complexity of VC class something in the order absolute constant over epsilon squared d log 1 over epsilon plus 2 over epsilon plus log 4 over 1. So this is approximately the number of samples you need to select to ensure that the empirical averages differ from the probability that the empirical average is different from the actual average. By more than epsilon is smaller than delta. If you get a sample large enough, you're fine with probability 1 minus delta. Now, as you can see, these terms are not that significant. They're logarithmic in 1 over epsilon and 1 over delta, and people tend to sort of ignore them for practical reasons. So the leading term is something like the VC dimension over epsilon squared. That's what you get. Now, two ways one can think of improving this, maybe slightly, using this proof. One would be, or the one would be, is that the fact that we used an infinity bound here, where we actually needed an N1 bound. Okay? We might have gained something. That's one I want to mention. The other thing which is very important, all I've told you is the following. If you have a VC class, then you can do this to a certain extent efficiently. What happens if you don't have a VC class? Well, the other part of Dr. Germanakis' work was to show that if you don't have a VC class, if your class has an infinite VC dimension, you can get arbitrarily large combinatorial cubes, then this doesn't have to tend to 0. Then this doesn't have to tend to 0. You can construct a measure for which this is bad. And I'm going to show that it's in the notes. But their work in 71 was essentially solving the problem of the uniform law of large numbers for Boolean classes. They said the uniform law of large numbers hold if and only if you have a VC class. The point I want to emphasize is that the rates they got, the quantitative result is fine. The rates they got are way off. You can get much better rates in general, okay, for our problem.
What do you define as a rate?
The dependence on epsilon and delta. Okay. So, and the reason is, you just have to be fair. Dr. Germanakis' work wasn't done for machine learning, right? Only in the, I guess, late 80s, people in machine learning started to use their result as something useful for us. But what they did was to find a necessary and sufficient condition for uniform law of large numbers. Okay? And they did that. They didn't need anything else. Using the combination of this lemma and this lemma together, they had the sufficient condition and use a different argument to get the necessary condition. They didn't bother about traits at that time. Okay? So, she made it not get involved. Okay, that's one thing I mentioned. Now, as I said, there is some hope of improving this using L1 covering numbers instead of L2 covering numbers. And I'm going to mention a result. I'm not going to prove it because I won't have time. It's a really, really beautiful result. I need that. So Lapping and Germanicus proved, using this lemma, that n epsilon f, an infinity union, an infinity covering numbers, they proved something stronger. They proved that the cardinality of the class is bounded by En d over d for an epsilon. Now, the reason I'm not so happy about this is, look at the way the logarithm of the covering numbers grow as a function of n. Okay? If you look at the logarithm of the covering numbers, you get something which is of the order of the VC dimension times log n. Okay? The question is whether you can get something in other modes which doesn't grow with n. And the answer is yes. So, Dudley and then Hausner prove that you can. But in fact, if f is a DC class, then, well, this is Hausner's formulation, then the covering numbers in LP, so n epsilon f and LP then are bounded by an absolute constant d to the power d, 1 over epsilon to the power. The notes I have the exact constants, but I'm not going to bother with that. Oh, sorry. To the power d for e to the power. Okay? This tells you that if you look at the log covering numbers in LP spaces, what you get is something which is of the order a constant which depends on p times d times log 1 over epsilon. Okay? So you get something which is completely independent on n. The size of the sample doesn't appear. Okay? So although the infinity covering numbers might grow as n grows, at a rate which is something logarithmic n, the L2 covering numbers don't, and you can plug that in here and get a slightly better result. But I don't want to do that. No, I'm not going to prove this. This result is slightly weaker than that. It has an additional logarithmic factor 1 over epsilon. Slightly proof is relatively easy. That's what you have in the notes. Hausner's result was just removing this extra logarithmic factor, and that's really good. A really, really good result. And I certainly like to show that. So now the natural question is, how to extend this Boolean case into the real value case. And we started with a class of real value functions. I want to show how to extend it to a real value case. So first I want to give a different interpretation for the VC dimension. Okay? What does it mean for a set to be shattered? Okay? This is the set. This is 0, this is 1. And now I'm going to look at the line which is half. What does it mean that I can get the combinatorial cube on these four elements? It means that I can get any combination of 0 and 1 I want. Right? So I can get, for example, 1, 1, 0, 0. Or so whatever I want. Okay? Now, 1 is half plus half. Oh, so nothing very deep. 0 is half minus half. This means that I can get, if I look at this level of half, I can get every combination of above half and below half by a margin greater or equal to half than I want. Right? It means that for every, if you look at 1 and you write it at half plus half, it means that I can get, for every subset, let's assume that this subset, I want it to be 1, I want to find a function which is 1 here, and 0 here. This is equivalent of saying that I can find a function which is over half on these points and below half on these points. And since my class is Boolean, so I know that the values I can get are only 0 and 1, I don't have to specify by how much over half or below I am. Since I know I'm over half, I have to be 1. Okay? So another definition of the VC of being shattered means Sn is shattered. It's shattered by F if it's not the same thing. If for every subset I there is some f in F depends on I such that f of xi is greater than 1/2 if I is an I, and f in xi is smaller than 1/2 if I is not. Okay? So for every selection, I corresponds to the set of elements for which you want to be 1, and its complement is the set of elements for which you want to be 0. So all I'm saying is, no matter what partition of your set of this set you take, you can always find a function which is larger than half on the element you selected and below half on the complement. Okay? This is exactly the same as you can get every combination of 0. Now what I did here is I used the following fact. I used the fact that once I know that I'm over half, I have to be 1. And then I'm below half, I have to be 0. But if I try to extend this to a class of real valued functions, I no longer can do that. Okay? I can no longer be certain that I get something which is greater than some level than I have to be. So another parameter has to come into the game, which is how far away from this level I am. In this case, so let me write this, I'm greater or equal than half plus half, and I'm less or equal than half minus half. This is the level. Okay? This is the margin. This is the level that you're looking at. You're measuring how far away you are from the level half. And this is by how much you differ. You have the margin of half above and half below. Now, using this, I can try to extend this to the real value case. Okay? So let's look at the real value case now. So now I have a range. My range is, let's say, 0, 1. I can get any value within 0 and 1. So now I want to sort of generalize this thing to the real value case. The way to do it, I need to specify two things. First of all, here, I was completely indifferent to the level I selected. I was even able to select the same level for every point here. I don't have to do that. I could have specified different levels. Right? I didn't have to pick that, to measure the margin away from half everywhere. So the first step is to select levels. Okay? The second thing which is different is that here, if I knew that I was above a certain level, I had to be 1, and if I was below a certain level, I had to be 0. So I didn't have a choice. But here, I want to specify how far away I am from the level. This is sort of something called a scale-sensitive parameter, which measures, you fix the level, you want to ensure that you're away from that level. So let's assume that this is the level. So I'm taking certain epsilon, and I'm looking at sort of an epsilon margin away from all the levels of the paint. Okay? Now, what I want to do is to define shattering at a scale epsilon, which is simply saying I can get every combination of above this margin, below the margin. Right? Just like here, I got every combination of above half, below half. Now I can get every combination of above this, below this. Okay? So the formal definition, that F in the class function, class, and that N be a set. Set A is excellent shattering. This is important. Epsilon comes into the game. Right? Epsilon shattered by F. If for every subset I in A, there is with the property that if there exist numbers Si such that for every I in A, there is some F in F with the following property. Fi Xi is greater or equal than Si epsilon if I is in I, and Fi Si is less or equal than Si minus epsilon otherwise. Okay? So the number Si's are just the levels. Right? You fix your levels. Epsilon is a parameter that somebody gives you, that's the margin you want. Okay? So you fix the levels, right? You fix the levels, and somebody gives you the epsilon, and you want to say, am I shattered? Okay, I am shattered if I can find good levels, in the sense that for that levels, if you take the margin epsilon away from those levels, you can get every combination of above below. So this is just a generalization of the VC dimension. if you take the VC, if you take a Boolean class of functions, the fat shattering dimension at level half is exactly the VC dimension. Okay? So that was the generalization. It was, I mean, this is sort of the latest generalization. The first generalization was that all the levels are the same, just like I draw here, half. It's called leverage fat shattering dimension. And it was used both in machine learning and to solve some nice problems in Banach space theory. Of course, the machine learners didn't know about people in Banach space, and the people in Banach space didn't know about people in machine learning, but they both used the same trick. And then people realized that the right way to do it is this: not to impose a level, a certain level, but to allow the levels to change. And there's a geometric reason for that. I'm not going to get into it. There is a reason why this is the right way, not the same way. So let's go back to this one, what we have here. I want to be able to show whether I can use this definition to estimate the coming weight. Okay? That's what I want. That's the only reason for introducing this definition. And the way it was used first in that way was, I think, in 1995, maybe 93, by Almond Machine, Bianchi, and Hausberg, who used this result to show the following generalization of the Vapor-Chervonenkis theorem. So they proved Almond and Hausberg that let F be a class of functions bounded by 1 then is a uniform event contained class if and only if for every epsilon greater than 0 fat epsilon f is smaller than infinity. And I have to tell you what fat epsilon if I forgot to do that. Just like in the VC case, the VC dimension was the cardinality of the largest set shattered by the class. The fat shattering dimension of the class is simply the cardinality of the largest set, which is epsilon shattered by the class. Generalization of the VC dimension. This is a completely analogous result to what Vapor-Chervonenkis had for the VC dimension. They had F satisfies the uniform law of about numbers, which is this, if and only if it has a finite VC dimension. If you're in the Boolean case. If you're in the real value case, this is true. The last thing I want to show you today is estimates you get on the fat shattering on this term using the fat shattering dimension. But again, let me point out that the main importance of this result in my eyes is not the quantitative result. Okay? They did it exactly in the same way. They used an infinity covering numbers which are known to be loose. They used this method which is loose. They didn't know it, but it is loose. And the bounds you will get in terms of the fat shattering dimension are suboptimal. Both the fat shattering dimension and the VC dimension are parameters which describe the uniform quantitative property from the qualitative point of view. Okay? There's necessary and sufficient conditions to ensure uniform dynamical containment. They're not the right parameters to capture the sample complexity. In the next two lectures, I'm going to talk about what I think is the right parameter to do that. But I'm going to convince you that these are the wrong parameters. Now, the way their proof goes, the fact that it's a necessary condition is exactly the same as the proof of the general case. Nothing changed. The fact that this is a sufficient condition was to do something similar to this, more like what Vector and German Engels did with an infinity covering numbers, and then obtain L infinity covering numbers using the fat Shattering dimension. And the result they had was the following. So, again, same result, same authors. There is an absolute constant. C such that for every F, say if Gauss function is bounded by 1, log n epsilon f n infinity un is bounded by C fat epsilon over 8 log squared n every f every measure. Okay, so you get that the entropy, the log covering numbers, are something like the fat Shattering dimension, the scale proportional to epsilon times the factor, the growth factor, which is something logarithmic in n, log squared n. Now, whether or not you can remove, remember in the VC type result, what we had was an absolute constant times the VC dimension times something which behaves like log n. Whether you can take the log square n and make it into a log n is an open problem. Nobody knows how to do it. You can slightly improve this. You can slightly improve this. Oh, by the way, just once you have this, you plug it into there, you're done. You get this. Another problem which was open for a long time, since they had this, was whether or not you can remove the n if you're not looking at an infinity result. And the best estimate, and it's almost optimal, is something that Almond Machine and I did a few months ago, which says the same under the same conditions for every p. For every p, log n epsilon f LP is bounded by some absolute constant times p squared f epsilon over a f times log 2 epsilon. So until the first step, which I did 3 years ago, was to show that if you change L infinity to NP, you can change this n to the fat Shattering dimension. And in some sense, the right dimension to look at things is the fat Shattering dimension of that scale. And later we were able to remove that and get something which doesn't depend on anything. So what you get is that the entropy in LP, the log covering numbers in LP, are something like the fat Shattering dimension at the scale proportional times log squared 2 over epsilon, and again, whether to remove this, nobody knows. The last result I want to mention, and I want you to remember that, because this is sort of the argument I'm going to use to convince you that this is a bad way of doing things, is the following estimate, a sample complexity estimate for classes with fat Shattering dimension. So if you take this result, combine it with this, and this is almost tight, you can show that the best you can hope for is to remove this square and make it into a log 2 over epsilon. So this is the best you can hope for as the covering numbers go. The best you can hope for in a sample complexity estimate in this way is to show that supremum or probability, whatever it is there, that's right, supremum greater than equal to epsilon less than delta, provided that n is greater or equal than some absolute constant over epsilon squared times fat at scale, so on the way of f log squared 1 over epsilon slope toward that. So let's, for a moment, that's the last remark I'm going to make. Let's ignore these logarithmic factors. We don't play a major thing. Assume that fat epsilon behaves like 1 over epsilon to the power. I haven't talked much about examples. Maybe I should. Maybe I will present some examples for fat Shattering dimension. But this is a natural case. All the interesting real valued classes which are defined by being sufficiently smooth or something like that, they satisfy this. Okay? The exponent change. They're essentially the fat Shattering is 0.1. This gives you an estimate of the sample complexity, which is of the order up to a logarithmic factor of 1 over epsilon to the power 2 plus. What I'm going to do in the next 2 lectures is to show you that using a different method, under the same conditions, you get a sample complexity which is of the order of 1 over epsilon to the power maximum of 2. Okay? For this. Afterwards, I'm going to show you that if you're not taking this approach, but taking the first approach, that there exists a function which has a small empirical error, but you want to put the probability of a function with a small empirical error but a large actual error, you get something which is even better. Okay? So this is what was known up until about 3 years ago. Then people started to use a different machinery which gave much better results, and that's what I'm going to talk about tomorrow. Okay? Thank you.